Right. So this is the last chapter of mechanics. With this, mechanics will be completed. We waited for differentiation and integration just to explain a few concepts that we are dealing with in this particular chapter. What we know so far about motion and mechanics is we know that so if I draw a displacement time graph, and let's say it is a linear graph with a constant slope. Let's say I'm starting from 10, and let's say somewhere here is 30, with amounts of time. Let me say this is 5 seconds. How would I work out the velocity from this graph? Somebody tell me what is velocity on a speed time graph?
That's not speed, that's displacement.
I'm sorry, velocity on a displacement time graph?
Displacement over time.
Displacement over time, or the gradient of your displacement time graph would give you the value of velocity. When you think about it, it works the same way, because basically what we are doing is, if I have to do displacement over time, what I do is my initial, so I'm going to call this as x1, and this would be my x2, this would be my y1, and this would be my y2. And to figure out the displacement, I started from 10, I have reached 30, so the displacement would be y2 minus y1. The total time I have taken, that would be 5, which is x2 minus x1. Does y2 minus y1 over x2 minus x1 remind anything from GCSE? That is your gradient. So the gradient of the displacement time graph gives you velocity. So the gradient of displacement time would give you velocity. In the same fashion, what do you think would be the gradient of velocity time graph?
Displacement.
Acceleration. Okay. So if I give you, so this is a displacement time graph, but let's say instead of your displacement time graph, rather this was a velocity time graph with, let's say, can you work out the acceleration at this point, please? So we know the basic idea of acceleration is, it is the change in velocity over the change in time. Your change in velocity is, should I do 50 minus 10 or should I do 10 minus 50? Sorry? 50 minus, how many of you think 10 minus 50? You can raise your hand. And how many of you think it's 50 minus 10? Acceleration. Now, whenever you do a change in anything, if you remember in science, it's always the final thing minus the initial thing. Remember this from you always. Whenever you're calculating the change of anything in physics, chemistry, biology, or in math, you always do the final minus the initial. When we start the journey, my initial velocity is 50. And when this journey ends at 10 seconds, my velocity is 10. So always do final minus initial whenever you're doing a change for anything. So the final time is 10 minus 0. So that would give me minus 40 over 10, which would be minus 4 meter per second squared. The fact that you've got a minus here represents you're decelerating, and you can see from the graph you are slowing down. So you have a negative gradient here, and that kind of fits together with the geometrical idea. Because the line is going down, you have a negative gradient, and it goes along with the fact that gradient of your velocity time graph would bring the acceleration as well. So the initial ideas for this chapter is, if you have a displacement time graph, if you take the gradient of the displacement time graph, you get velocity. If you have a velocity time graph and you take the gradient of the velocity time graph, you could figure out what is acceleration. So it's something that was already there. Maybe we haven't seen it so far. It comes from the idea that when you try to calculate this thing, we are basically doing y2 minus y1 over x2 minus x1, which is in fact the gradient that we know from GCSE. So this is GCSE. Now, how to extend this idea to the A level? Now, let's say instead of a linear graph, this time in place of, let's say you have a velocity time graph which is not linear, this time you have a slightly so let's say this is part of a, we're not taking the negative side, but what kind of a shape is that? That's a quadratic. So it's not a linear one, it's a parabola, so that is a quadratic. So if I have to define this graph as a function, now remember in pure maths we always do y equals f of x. Have you seen this?
Yeah.
Pure maths. So my y here is v, my x here is t. So I can write v as a function of time. When I say a function of time, a function basically gives you an expression. So I can say v is equal to some expression of t. What expression would I write here?
The equation of the line.
Sorry?
The equation of the line.
And what is the equation of this one?
X squared.
T squared. Now imagine from GCSE, if I had given this question to you in GCSE without the y and the x, and if I had asked you what is the curve or what is the equation of the curve, you would have said y equals x squared. We're using the same idea. In place of, we're skipping the negative part. In place of y and x, we are doing this on a velocity time graph. So you have v as your y and t as your x. So I can say v here is equal to t squared. Okay. Now what does this mean? That means if I have to find, or if I want to find the velocity at any point, that means I can use this expression and say, at time t equals 0, v is equal to t squared, which is 0 squared, and that is 0. At t equals, let's say 3, v would be equal to 3 squared, which is equal to 9. So when you have the velocity as an expression of time, you can use your time values to work out the values of the velocity at any given time. Okay? So that is a slight extension into GCSE. Into A levels. Now the next idea is, we discussed that gradient of velocity time graph would give me acceleration. But I know how to do y2 minus y1 over x2 minus x1 if it was a straight line. But what would I do with the curve thing? You would? You would differentiate it. That is the whole idea of differentiation. What differentiation helps you to do is, let's say I want to find the acceleration at, let's say, this particular point P. To find your curve or to find the gradient at a particular point P, what we are doing is, we would draw a tangent to that point, and we're going to measure the gradient of that tangent. Has Miss explained all of this?
Yeah.
Yeah, so you know the idea. So what we are doing is we are measuring the gradient of that tangent, and you would make that line as very small as possible. Why do I want to make that line as small as possible? It would be more accurate, because what happens if the tangent line that I'm considering is slightly longer? I could do the gradient for this one as well. I can do y2 minus y1 over x2 minus x1 for the large triangle, but what is different about the large triangle and the small triangle? When you look at the large triangle, does it look anything like the curve that you've got? No, it's kind of deviating too much. But if you look at the smaller triangle, that is kind of like okay-ish, fitting into your curve. So it is always better to use the smaller triangle or a smaller tangent line to measure the gradient rather than using the longer one. And that is where the idea of limit comes in. We say limit h tends to 0 because you're trying to make that tangent line as infinitesimally small as possible so that it kind of fits perfectly into the point. So that is where the idea of limit comes in. You don't have to worry about all of this. This is not pure maths. All you have to remember is, if you have to find the gradient at the particular point P, all I have to do is find the derivative of my function. What is the notation for derivative? dy over dx. Now, here I don't have a dy, so this would be a dv over dt, because you're doing the same thing. It's dy over dx. Y here is my velocity, x here is my time. So if I have v equals t squared, dv over dt would become, that would be equal to 2t. And then let's say if I go back to my picture and I say the point P has a time value of, let's say, 3 seconds. So if I want to figure out the acceleration at 3 seconds, I can figure out. So dv over dt, in fact, gives me acceleration is equal to 2t. If acceleration is equal to 2t, then I can say at time equals 3 seconds, the value of acceleration would be equal to 6 meter per second squared. So that is where differentiation and mechanics kind of comes together. Basically, we are trying to measure the gradient of the curve at this particular point. Because it is not a linear curve, we are going to use the differentiation to figure out the gradient of the tangent line. And once you have the gradient of the tangent line, you can then plug that in for the expression there. Last thing that I want you to remember. Now, these are like extreme cases. When something is at rest, that means when something is not moving, what will be your velocity? 0. So if you want to check if something is moving or not, all you have to do is check if the velocity is 0. That's one idea. When you are moving at a constant speed or at a constant velocity, what would be equal to 0? Acceleration would be equal to 0. Why would that make sense? Because if you think about it, expression-wise, we know acceleration is change in velocity over change in time. When you're moving at a constant velocity, do you have a change in velocity? No. So your acceleration would be 0. Geometrically speaking, if you say this is your velocity time graph, I know that gradient of the velocity time graph would be equal to acceleration. What is the gradient of this line?
0.
The gradient of a flat line is 0. And so that also fits in perfectly to the idea that acceleration would be 0 when you're moving with a constant velocity. Last thing that I want you to remember, let's say you have a velocity time graph with, let's say this is a cubic expression. So I'm going to say velocity is equal to t cubed plus 2t plus 3. Is there anything that I can do to find my initial velocity? Initial velocity means what in normal English? At the start. So at the start, t is equal to 0. So if you want to find the initial velocity, initial acceleration, initial anything, all you have to do is put t is equal to 0 into your expression. And you can see when you put t is equal to 0, you get v is equal to 3. So those are the